Let's see. Hello, everyone. We're down to 5 minutes or so to start at noon. Can I get a quick check mic on the chat? Oh, there you go. I got Connor. Good. I'll be right back. Tell my kids to log off any devices. All right, coming up. Maybe give it another couple of minutes for folks to join. Oh, quote of the day: "The time you enjoy wasting is not wasted time." It is by a quote from my favorite philosopher / logician, Bertrand Russell. He has many interesting quotes that I encourage you to check out. But this one is my favorite because it's basically how I justify the many hours that I spend playing Apex Legends lately. Very academic way to justify my wasting of time on video games. Okay, Google, stop. Yeah, that's so. This quote for Bertrand Russell is definitely out of context in the course. you don't wanna apply necessarily this for the course, or do so at your own peril. Um, okay, I'm just tried. Oh, Apex has been out for I think it's this month. It was the 2 year anniversary or something. They've been playing it for the full 2 years. Love that game. Spent way too many hours playing Apex Legends. Play with my kids. My 14-year-old is way better at it than I am. Um, all right, let's see. We're coming at 2 after 12, so let's get started because so hopefully this time around we don't have technical issues. I've kind of updated some configuration in my router to basically give priority to my laptop that's doing the streaming. So hopefully we don't run into any issues. I think it was more of an Xfinity type of issue at the time because honestly I hadn't seen that before. But still, just to make sure. So last time, run into some technical issues, put us a bit behind. So even though today's lecture is lecture 9 on ordered and sorted ranges, before we started, we need to finish the previous lecture, which is we still needed to cover heapify and heap sort, right? Heapify specifically is particularly important for Project 2. And basically the last lecture that we had, lecture 8, you heard me say throughout the lecture, is very important for Project 2, which is now out. So again, do not apply for the quote that's on the slide for Project 2. You want to start as early as possible, get you submitted to the autograder as early as possible. Yeah, let's get started. Just to finish off these two topics. Now, if you recall, last time, heapify is a way in which I take some array or vector. Again, I use those terms interchangeably, vector, array. Take a random, say they're integers, right? They're all in random order. And I pass it to this heapify function, which when it comes out, when the array comes out of that heapify function, it's now going to be an array that follows all the properties that I need for a heap, right? Namely, it represents a complete binary tree where each node satisfies the heap order property. Okay, so that's the point of the heapify, and we spoke about the fact that, and that's a summary there. We spoke about the fact that there's basically 4 ways that you can do this, and basically only one of those 4 is what you would want to do. 2 of them do not work, flat out. They do not work. 2 of them do work, but out of those 2, you only want to use the one that's fastest, which is what we call the heapify function. And that is where you proceed bottom to top, doing repeat fix down on the array. Okay, when bottom to top is kind of the tree view of the heap. If you're looking at it from the array point of view, which is what you're using to implement, then what you're doing is just traversing the array right to left. Okay, if you remember, go back to the previous lecture and all the properties that the array would obey behind the scenes as long as it's following the heap order property. It means that the second half of the array is basically all the leaves, okay, in the tree that represents the heap, and then the first half would be all the internal nodes of the heap tree. Okay, and again, we always made the difference between representation with a tree, but implementation was just using the array. Okay, just because it's way faster. Yes, you could implement it using your good old, tree node implementation, but then you'd have to traverse nodes and all that stuff, and you can't take advantage of random access. So, kind of the ideal way to implement a heap tree is using an array. Okay. All right. So let's look at how this works, and then I'll convince you that the runtime of this procedure is in linear time, right? Which is quite interesting because you would expect it to be something like n log n, right? Because take the last bullet point there shows the other way that it would work, which is to do top down, meaning traverse the array left to right, or iterate over the array left to right, doing fix up. That would work, but that would give you a runtime of n log n, right? And that makes sense because if I'm doing fix ups, and each fix up is worst case log n, and I'm doing n of those, then it makes sense that it's n log n, right? Nothing too complex about that runtime. But then if you look at the first bullet, what we're doing is also iterating over the array, doing fix down, which we said is also log n time. So how come there we arrive at a linear time runtime rather than n log n? And that's what we're going to talk about, because it's not trivial to come up with that. All right, so here's the procedure that we're going to do. There is both our tree representation on the slide, and also down below is the array representation. Okay, and so what we're going to use is bottom up, fix down. Right. Again, bottom up is nothing but I traverse the array right to left. And if I were to traverse the array right to left, I would immediately see that there's no fix down that I need to apply for one half of the array because it's all leaves. Okay, remember the right half of the array, all leaves, there's nothing to fix down. Remember, fix down would move the nodes, would swap with one child all the way down until it reached the bottom. It's already the bottom. There's nothing to swap down, right? So nothing to do. So in fact, our loop can just start at half of the array, right? It don't even need to start at the rightmost element in the array. And so the first node that I would check whether I need to fix down is 1, is the node that contains the value 1, which would be the node indexed by 4. Okay, just to make that distinction, because it's confusing that the values contained in the tree are integers, but we're also using integers for indices. So the node index at 4 has value 1, and that's the one that I would try to fix down, which indeed I would pick the max out of the 2, which would be 81, and I'll swap with that, right? And then the next node that I would check would be 5, because that's the next one up, right? The node that has, so the node 3 that has value 5, and then do a fix down there, which would make a swap with 14. Then the next node that I would check that has value 2, and it also happens to be node 2, I check that one and of course pick 81 to swap with. And then lastly, I check, there's one more. So fix down had not done its work by doing one swap. It needed to do 2 swaps at that point, and then it's all done. And then we would check the root node, which contains value 4, and decide that I would swap with 81. Still not done. That might require another swap with 18, and at that point it would be done. Okay. Cool, and that would be our procedure. So notice that we really only iterated this. Oops. We only really iterated on this half. Okay. Doing fix down all along. And if you notice, you see that a lot of them, I only needed to do 1 swap. Other times I needed to do 2 swaps, right? With the fix down call would cost 2 swaps. And at most, the fix down would cost 3 swaps. Okay. So that's the rationale that I'm going to use to come up with the linear time runtime. Is I'm going to count how many possible swaps can the fix down be doing, okay, at each point. All right, so that's my tree right there. So now let's go about our business. So this is the let me go back. This is the array representation. Means like I'm done with half of the array because they're all leaves. No need to do anything there, right? I check 1. I compare against the 2 children. Pick 81 to swap with, and the animation does that really nicely for me. and then check 5 against 9 and 14, and so on and so forth. Okay, so it's basically the same thing that we did with the tree. I like the tree representation better. It's nicer. But of course, the actual code would be using arrays, so it's particularly relevant as well. So then we're done. Okay, so now let's look at, in terms of number of swaps, how much work is actually being done by this particular heapify function. Okay, so let's say if we're counting how many swaps we would need to do if we're doing fixed down on the leaves nodes, well, that's easy. That's 0 swaps because they're already leaves, right? And there's half of the nodes in the tree are leaves. Okay, so basically a big chunk of the nodes don't really need to do anything. Okay? Then for n divided by 4 leaf internal nodes, I'll have a max of 1 swap, right? Because if you look at the tree representation, it'll be the next level up, and there's only one possible fixed down swap that you could do, because the next level that you run into is the leaf, right? Is the bottom of the tree, is where the leaves are at. So you cannot do any more swaps down. Okay, and then say one level above, then I'd have n divided by 8 internal nodes there, with potential number of swaps being 2. Okay, so that gives a total of swaps for that level, right? 2 nodes times 2 swaps gets 4 swaps max, right? And then similarly at the top level, I have n divided by 16 internal nodes with a maximum of 3 swaps each. And that gives you, well, topmost level, just given by the size of this tree, only has 1 node, which is the root node, times the 3 possible swaps, worst case, that you end up doing. That gives me 3 swaps max. Okay, and if I add all that up, okay, then you see that the total number of nodes roughly is going to equate the number of potential swaps that you'll have to do. In fact, it's always a little bit smaller. Okay, the number of swaps as compared to the number of total nodes in the tree. And you can generalize all this math, right? So instead of, you have n nodes with k levels, right? And then you come up with all the math for doing it, and it'll come down to being linear time. So that's how you get linear time for this approach, right? Whereas with other approaches is n log n. Okay, so very, very efficient method. So I'll leave it as an exercise to generalize all this math. You can also, I believe CLRS has a nice discussion on this, where all the math is worked out for, again, any generalized tree with n nodes and k levels. Okay. All right. Let me quick check on questions. Oh, by the way, and I think that was in the previous slide, right? Let me go back. Oh, this is a lot of animation. See if I can jump real quick. Yeah, this that we just discussed, the implementation in the STL for this function is called make heap. So it's not called heapify. It's just called make heap, and it works on any vector. It might also work for other types of containers. I'm not sure. You'd have to check. Very sure it works on vectors, and what you'll be using in project 2 is make heap on a vector. You would pass it iterators, the begin and end iterator of the container. Okay, I think that was a question that was asked. Oops. Dex might work, but again, you'd have to check. All right, so that's heapify. Now heap sort. Okay, so if I ask you, so given a heap, if I and usually do this when it's like live lecture in person, like we do it as an exercise. All right, so you know what a heap is. Give me an algorithm for sorting using a heap, right? So If I give you a vector of random integers, develop an algorithm that uses a heap that gives the output the same vector but in sorted order. And so you would say, well, I mean, if a heap, all I got to do is push a bunch of stuff into it, and then I can easily get whatever the max, again, assuming it's a max heap. And I would, every time I pop, I would just get whatever the max is. Then all I need to do is push everything into the heap, right? And then pop everything out, and everything's going to come out in sorted order. And there it is. That's my heap sort algorithm. And in fact, yeah, that's basically how heap sort works. But in the explanation that I just did, notice that I had to use an extra vector, right? Because if I have my input vector that contains all random ints, that is separate from the internal vector that's going to exist inside of the heap that I'm still going to need because, as I said, I would push everything that's in the first vector into the heap, right? So the heap will need to fill all the way up, and then I pop everything out, and everything will indeed come out in sorted order, but I ended up using linear space, okay, with that extra vector that I used for my heap, okay? Also, the runtime would be n log n, because I will spend n pushes into the heap, and that's already n log n, and then I'm going to pop everything out. That's another n log n, which overall runtime is to be 2 times n log n, but O of n log n. Okay, so that would be a heap sort algorithm, straight up. But we can do way better, because what we can do is effectively reuse the same vector that's given to us to do heap sort, right? So rather than using a separate heap container, okay, to push all the elements in there, I can reuse the same vector that I'm given, okay? And this works specifically because we have the heapify function, right? So this heap sort algorithm, if you see line 2 right here, first thing it does is like, all right, I'm just going to heapify the same vector that I'm given, or the same array that I'm given. That's actually what we're using here, an array rather than a vector. Just heapify. All right, so now I have my heap, okay? But I still need everything to be in sorted order, not in heap order, okay? So what I would need to do is something very similar to heapify, except that before I call fix down, I do a swap, okay? Because notice what I would want to do is like, all right, so my max element, I know where it is, right? It's the very first element in the array. So I know that's the max, so I just swap it with the other end of the array and then call fix down on it. Okay, so that's what it's being done here in line 4. You're doing the swap with, you're swapping whatever the max element is and put it at the end of the array, the current end of the array. Okay, and then from then on out, I would just fix down on that where the current max is. Okay. So this is easier to see with a neat animation, right? So let's look at it. This is both my tree heap picture and also my array heap representation. What I would do then is, I'll just take the root. So the root right now is 81, and the last element in the array is 1, right? So I'm going to swap 81 and 1. So I do that swap, and then all I would need to do is call fix down all the way from 1 through 8. Okay? So then after that's done, then I would swap 18 with 2 and then call fix down. Notice that the fix down, and I'm skipping all the fix down swaps that would happen, right? Because otherwise this animation would take forever, right? But if you see, 2 was here after the swap, and I would call fix down, and then it would place it all the way down here, right? This is where 2 is now at, okay? And then I'd be done with that. And then I would swap now 14 with 5, place 5 at the beginning of the array, and don't call fix down again, puts 5 down here, right? Then I'd be done. Then move, swap 9 with 2, okay? Fix down, moves 2 down here to the indexed at 4 now. And then, so, we would just rinse, repeat, okay? All the way down. So effectively what we're doing is the same approach as we described earlier, except we're using the same array that we're given as input to also store the elements that I'm effectively popping out of the array, right? But we're not really popping, we're just swapping, okay? So that's how heap sort works. And so now, instead of having a linear space algorithm with an n log n runtime, I have a constant space algorithm, but I'm still at n log n runtime, right? There's no way to get around n log n because I have a for loop, and inside of the for loop, I'm calling fix down each time, okay? And yes, that the fix down in this case would be log n time, would be considered log n time. Cool. And then the other work that I did in my heap sort algorithm is the heapify, but then that means that overall I just have O of n with the heapify plus O of n log n, which is n log n, right? Okay, because this right here is O of n log n, O of n, and then this right here is O of n log n, okay? For a total of n log n, okay? So that's, this is the problem with having animations. To find a different way to jump to. So that's our summary for heap sort, okay? You given n elements in a vector or an array, you first convert to a heap, okay? Using your heapify function, okay, which just takes linear time. Then conceptually remove elements one at a time. So pop every element one at a time from the heap, except that if you go back to the code, we're really not popping. All we're doing is swapping to store whatever was popped, okay, in the same array. So what you're doing is removing by just swapping and filling the original array from back to front, okay? And that's, that's the algorithm, fairly smart algorithm. So it's an n log n sorting algorithm, which we consider to be an efficient sorting algorithm as compared to elementary sorting algorithms, which we'll cover in the next lecture. We'll start covering in the next lecture. Other examples of fast or efficient sorting algorithms, which we will discuss, are quicksort and merge sort, and we'll compare, each one of these algorithms in turn, and we'll dive deep into what each one of these algorithms do. Okay, so fairly cool algorithm that takes advantage of a neat data structure. Okay, all right, so that's it for heapify and heap sort. Let's see, we're done now with lecture 8. I'm gonna close this. Discard. All right. Bear with me while I open the slides for lecture 9. All right, I think we're good now. Oh, that's not what I want. You're all seeing the presenter view. Well, that's not good. I'll just do that. Then I have no percent view. All right. So before I move along to lecture 9, let me make sure. So I don't know if do we have anyone from staff today answering questions? Hopefully. Not, I'll try to ping someone. Let's see. Wait, which version of heap sort was O of n then? So no version, it was O of n in terms of space. Okay, notice there's always the space complexity and the time complexity. The first algorithm that I described, I didn't give code for, right? It's kind of the algorithm that you probably would have thought of if I assigned you the task of like using a heap, give me a sorting algorithm, okay? That will require O of n extra space, okay? But it's still O of n log n total runtime, okay? There is no linear time heap sort algorithm. Heap sort is considered an n log n algorithm. It does, if you look at the code, it does use heapify function, but the heapify function just does take linear time, right? But then because you have the for loop that calls fix down, the overall runtime is still n log n. Okay. I think we just said, okay. Oh, and I guess I answered it again. Okay. Heapify, why use this instead of merge sort or quick sort? The space benefit, yes. So Owen, we will get to talk a lot about that in later lectures. There are instances in which you would want to use heap sort over merge sort or quick sort, but most of the time in practice, you would want to use quick sort. There are specific situations where you can only use merge sort, which again we'll talk about. We haven't seen any staff in the chat yet. Yeah, it looks like. I'll try to ping someone, but if not, then I think we'd be good for today. But there's a heap sort that's in place. Yes, correct. Sahil, that was the algorithm that I gave you the code for in the previous set of slides. That algorithm is in place, okay? And notice that the big difference was with doing the swaps, right? The swaps will just move each of the maxes that you get on each pop and just move it to the back of the array. So you're basically reusing the same array in which you called heapify. Okay. All right, so let's move on to our next topic, which is ordered and sorted ranges. So this lecture is actually a mishmash of a couple of things that are quite important in practice. So when you go off in your careers, you will have to pay close attention to when the container that you're using to do whatever it is that you're using is, number one, whether it's ordered, number two, whether it's sorted. So ordered and sorted are not the same things, okay, as you're going to discuss, okay? All right. So far we've been using and reusing the term container for a lot of things, and really there's kind of no way to avoid it. I mean, in its most generic definition, a container is something that contains objects, so it holds objects in one form or another, okay? It could just be for storing variables, okay? Or it could be for storing more complex objects, right, that are instances of some class, so on and so forth. Now, the idea is if you're storing all these elements, okay, because again, whatever they are, whether just simple variables or primitive data types or more complex objects, right? So we just call them elements, right? If you have this particular structure that's containing this set of elements, you're facilitating a way to protect or control all those elements, okay? So that means that it facilitates, say, copying all the elements, making updates, modifying by maybe sorting them, right? Or do anything with this collection of elements or objects. So examples of these, so you're very familiar with by now, especially given Project 1. And then you probably already started Project 2, hopefully. Vector, deck, stack, map, list, array, they're all examples specifically STL examples of what we mean by a container, right? And you can have several types of containers. You can have a container where really you don't care in what order you're storing the elements, right? You just basically throw all those elements in the container, don't care, right? That's an unordered container. There are some benefits to using an unordered container, okay, which we'll talk about. Now you have an ordered container, okay, which is, hey, I'm placing these elements in there, but they should follow a particular order, okay? And the advantage there is that because the elements are following a particular order, then stuff like querying whether an element exists in the container is way easier, okay? Because we can rely on the ordering to do things a lot faster than if we have to assume that there's no ordering, right? So, well, if there's no order, all I can do is like search everything potentially till I find what I need. And then you have nested containers. We don't cover them here, but of course, you definitely use nested containers in Project 1, right? When you were declaring classes, and in there was a vector, vectors, and stuff like that, right? So, but there's nothing specific to say about a nested container other than you can declare them, and then you'd have to manipulate them in whatever way you seem fit. Okay. All right, so more specifically, types of containers that, with regards to the STL, right? So if you're searching STL literature or general C++ literature, there are these distinctions made about types of containers, which is, a container, just to say, call it generic, so plain container. That's going to support add and remove operations. That's kind of like the base level of operations that you would need to call your struct a container, right? You need to add elements, but you also need to be able to remove elements, okay? A searchable container would mean that it also implements some sort of find function or query, right? Depending on books, instead of find, I might call this query, right? Or just search. Okay? But it's just an operation where what you're looking to do is find some specific element that exists in the container, okay? Then there's sequential container that allows iteration over elements in some order, okay? So plain old vector is an example of this. You can iterate over the elements in the vector. I have often get asked a question like, well, isn't any container sequential then? Because I should be able to take any container and iterate over each one of the elements. No, for example, the STL stack or the STL queue does not allow you to iterate over the elements in the stack or the queue, okay? And there's reasons for that. It would basically violate the ADT for either a queue or a stack. So there's an example of when, even though behind the scenes a stack or a queue might be using a vector, the abstract data type of a queue does not facilitate a sequential iteration over the elements in the stack or the queue. Then there's an ordered container, which is a sequential container that maintains some current order, okay? Now, this is often confused with the mathematical term for the ordering of a set, okay? This, when we say ordering here, is kind of very STL specific, okay? So an ordered container means, and there's the example there on the slide, that it's like a bookshelf, right? If I have a bookshelf and the books are in some particular ordering, I don't know, by color or height. If I take one of those books out, that doesn't change the ordering of the rest of the books that are currently in the shelf. Okay, so same deal, but with containers, right? An ordered container would mean that in whatever order it has right now, if I take something out, that's not going to change the ordering of anything else that still remains in the vector or array, okay? And then there's a sorted container, which is a sequential container with a predefined order, okay? So you cannot arbitrarily insert elements, right? Because it would break the constraint of the sorted container. Okay, so that begs the question: which would sorted containers be preferred, or when, excuse me, would sorted containers be preferred over an ordered container? Okay, and the answer to that would be, well, if I know that in my particular requirements, I'm supposed to search this container quite often, and in fact, if I need to search it or call the find operation a lot more times than I need to insert into it, then a sorted container is ideal, right? Because if it's sorted, I could take advantage to do faster queries. Okay, and if you're thinking, oh yes, because it would be binary search, yes, indeed, which we're going to cover in the next couple of slides. But more generic, right? If it's some particular sorted order, that should allow me to do faster queries. Okay? And again, if in the requirements it's specified, well, I just have this pool of elements that you'll just store in memory, and then I really don't need to add, right? Let's say that if we're storing the cities in the U.S., right? Well, that doesn't really change that often, right? So I would basically load up my container with all the cities in the U.S. and I order them alphabetical order. Okay, so now it's sorted. And now if I need to query whether, some particular city is in there, is an actual U.S. city, then all I need to do is just do a binary search on my container, and real fast lookup will let me tell if it's a valid city in the U.S. Okay, and only now and then would I need to insert a new city. Okay, and so inserting will take call it a runtime penalty, because you need to insert in a way that maintains the sorted order. But that's okay, because most of the time I'm just doing lookups. So I'd rather do that. All right, so a quick clarification again on the what we mean by ordering. Okay, order containers, the elements in them maintain their relative position unless they are moved. Okay, so as I was mentioning earlier, if A comes before Q, and then you insert Z or Z, okay, then the relative ordering between A and Q has not changed. It's effectively the same. And the same also applies if we're removing an element from the container. Okay. So that's what we mean by ordering. The emphasis is that this is different from the mathematical definition of ordering, okay? Because, if you want to look it up, right, there's weak ordering, there's strict ordering. In fact, the heap ordering constraint that we talked about in the last lecture is an example of a partial ordering, okay? It just means that some of the elements follow a particular order, but some of them might not, okay? So that's what is known as partial ordering. But again, that's not what we're interested in terms of ordering. Is strictly container specific, which is what's described on this slide that I just went over, okay? And it's very relevant to STL, not the mathematical definition of ordering, okay? All right, so now that I know what differences between sorted and ordered containers, what if I want to implement such types of containers, right? Because yes, we have the STL. You might be like, well, why do I need to implement them if you said we have the STL deck and vector and so on and so forth. Why do I need to implement them? Well, because this is a fundamentals course, right? So you might, want to implement your own specific custom container, okay? Which in fact you will in project 2, specifically a bunch of priority queues. Well, 4, not a bunch. 4 is not a bunch. All right, so the two main types of implementations that we will focus on here is array-based versus linked list-based. Okay, array, if you recall, contiguous, slots in memory that are assigned for the array. Whereas a linked list is more like connected nodes that might exist in different spots in memory. Okay. Now, so which type of implementation you would pick, whether an array or a linked list, really depends on the context and the requirements that you have for the container. Okay. So you'd have to really think about like which of the operations, specifically the ones that I talked about in the previous slide, right? Which ones would I call more often than which others, than what other ones that I have? So I just gave an example with that for the U.S. cities, right? So it does benefit to study kind of multiple implementations that you can have for both, array versus linked lists, so that you understand the trade-offs and the benefits, so that you can make a good decision. So that begs the question: when would a linked list be preferred over an array? Okay, and this was maybe 2 lectures ago when we were when I was showing plots of vectors versus lists in STL, right? So we were discussing the performance of STL containers. I described the benchmarks, and one of the benchmarks was something like, well, if I just take my container and basically insert a bunch of elements in the middle, right, of the container, you saw in those performance comparisons that that's when lists would shine, right? And that's an example of a context in which you would pick a list over an array. And I mentioned last time, I'll repeat it, that's kind of our contrived situation. Like in practice, what you'd want to do is like implement your overall requirements such that you don't fall into a situation where you have to insert in the middle of the container, right? So basically, you would structure the feature that you're trying to implement. Say if you're implementing a feature for an app, right? You would decide like, well, I just rather redesign how I implement that feature so I don't end up having to insert in the middle of a container. You'd rather do that, which is why in practice, you often kind of end up staying away from lists and most of the time want to use arrays. But again, theoretically and for the purposes of fundamentals in this course, there are specific situations in which a linked list would actually be preferred. Okay. All right. So I'll pause here. Take a quick glance at the chat. You can pass a comparison function that tells heap sort how to sort. Actually, so I don't know if there's a heap sort STL. I don't. Can anybody check whether there is? I've never used it. If there's a heap sort STL function, I usually, well, not usually, always use the STL sort function rather than heap _ sort, if there is such a thing. So I'd be curious. But how does the reverse anything? Wouldn't that ensure the right order? Heap sort will start with a heap with the smallest element at the head, then sort by placing that at the bottom. Yes. And then because heaps are usually sorted max to min, does min to max by default? Well, this is kind of and I think Ian just checked. There is no heap sort in the STL. Thank you, Ian, for looking at that. But there is a sort heap. Oh, which I've never actually used either. So that's interesting. We should look this up for the course. All right. But most of the questions are about heap. So let me just keep going with sorted and ordered containers. All right. So here's the table comparing complexities of an ordered container that I might implement with either an array or a linked list, right? So the idea is to highlight where the trade-offs would be, right? Adding an element, remember, ordered container, it means, all it means is that, again, if I insert or remove something, the rest of the elements currently in the container, they do not change their relative order to each other. So an order container using an array, that's just going to be constant time, because all I would need to do is just place the element in an open position in my array. Okay, and I assume or we're going to take away the question of whether I have enough capacity in my array. We're going to take that question out of all of this, right? You assume that we have enough capacity, so all I need to do is just place it at the next open slot in my array. And then a linked list, that's just create a new node, okay? And then attach it to the linked list. By attaching, I mean updating the pointers so that you don't get a broken list. All right, now removal in an array is linear time, but this is assuming that what we want to do is keep an array as compact as possible, right? So this is removing a specific value, okay? So that would mean that I need to find the value that I'm looking for. So as long as find is linear time right here, down here, I remove val, which is again a value, that's going to be linear time, because I need to call find function to find a value that I need to remove from my array, and then remove the array. Sorry, and remove the element from the array. In a linked list, well, similarly, I would need to traverse to the value. Okay, same deal, because the find function is linear time. Removal of the value is going to be linear time. Then you have removing, but having already an iterator, meaning I already know what I want to remove, so I don't have to search for it. You might think, well, that's advantageous. That means that in an array, I can just go ahead and remove it. But remember, if it's, somewhere in the middle of the array, we're assuming that we're going to always keep the array as compact as possible. So if we remove it, we're going to have to shift all the elements by one, right? So that my array is always as compact as possible, and I don't have like empty elements in the array. Now, this is an example of when you might think back like, well, I don't want to spend that time doing, whenever I remove, I don't want to spend the time to shift all the remaining elements one to the left. Okay, so maybe I'll just change my requirements. Like, all right, so I won't shift. I won't do that. I won't shift all the elements. I'll just mark this element as deleted, right? So now I make things a little bit more complex, because I have to keep track whether an element in the array is currently deleted or not. Okay, and then I could make my remove iterator operation right here. I could make that constant time in my array. Okay, but again, for the purposes of the comparison, since we're not adding all this complexity about keeping empty elements in the array, everything's kept as compact as possible. I would need to invest linear time to make sure that that array stays as compact as possible. All right, and then a linked list. It kind of depends on whether I have a singly linked list or a doubly linked list, right? If it's a doubly linked list, it's constant time, okay? Because again, this is assuming that you're removing already having an iterator to what you want to remove. Remember, an iterator is really just a pointer, so you basically already have access to the node that you're looking to remove. Okay, so if it's a doubly linked list, I can just yank it out, fix my pointers, and I'm done. Okay, but if it's a singly linked list, I cannot do that. Okay, because if in a singly linked list, I don't have a pointer to the previous node, so I would still have to traverse my list to find what the previous node is to the current node that I'm looking to remove, so that I can fix the pointers properly. Otherwise, I end up with a broken list. Okay, so that's why it's linear time if it's a linked list. It's constant time if it's a doubly linked list. Find operation for a particular value in the container. That's going to be linear time for either an array or a linked list. Not hard to see that, right? Worst case, we assume last element is at the very end of the linked list or array. So worst case, linear time. Okay. The star operator for an iterator, which is just dereferencing the iterator. Okay, that's basically given a pointer to some element in the container. I want to look at the value, so I need to dereference the pointer so I can actually get access to the object. Okay, that is constant time, whether it's an array or a linked list. Okay, and then random access, which is the open and closing square brackets operator. Well, that's going to be constant time for an array because I can always just use pointer arithmetic, right, and jump to that element. Okay. Right, because the input to this is an unassigned int, unsigned int. So given that index, I can just jump there, remove that element. Okay, sorry, not remove it. Look at get access to that element. But then a linked list. Okay, that's one of the big disadvantages with a linked list, whether it be singly or doubly linked list. I don't have random access, right? I can't use pointer arithmetic because my nodes can be in different places in memory, so I can't jump to a specific node. I have to traverse my way through to that node. Then you have insert after, which is an operation where you're trying to do exactly that. You want to insert just before the given iterator. So notice this takes on two parameters. One is the iterator, and one is the value that you want to insert. The iterator is the node, basically the position in the container where you want to insert val. Okay, that position is given by an iterator. So in an array, similar to the situation for removal, it's linear time, and this is where a linked list would shine. This would be constant time. Okay, because all I would need to do is just fix the pointers, because it's insert after, and a singly linked list would always have pointers to the element that comes next, right? What a singly linked list would not have is a pointer to the previous node, right? But to the node that comes after that, we can easily access. So if I'm inserting after, that's constant time for whether it be a singly linked list or a doubly linked list. Okay. But insert before, right? That's something that's still linear time for an array. Again, same situation that we had for removal and such. But then in a singly linked list is different from a doubly linked list. If it's a singly linked list, it's going to be linear time. Okay. Singly. And in a doubly linked list, it would be constant time. Basically for the same reason than for the removal given an iterator. Cool. All right, so that's comparison of array linked list implementations for ordered containers. Okay. All right, so how about for sorted containers? Okay, so sorted containers, we're assuming that there's some particular constraint on the ordering. Okay, so the way to see it is sorting is a stricter ordering. Okay. It's stricter because whatever happens with the container, with each operation, I want to make sure that that constraint is maintained and I don't break that constraint. Otherwise, you'd have a broken sorted container, which is bad because then, it would just misbehave throughout. Okay. So adding an element is linear time. Okay. Adding an element is linear time because you need to find a position, given the sorted ordering, you need to find the right position at which you're going to insert the element, right? So it's similar to the previous case, okay? But then after that, we're again assuming that we're going to keep this array as compact as possible. So even if I would have, say, fast access to find the element, okay, which I haven't talked about, but in fact, for a sorted container, a find would be, way faster than in the ordered container, because if it's sorted, I can rely on binary search, which is log n, right, which is shown here on the slide. So let's just say that we have fast access. I still run into the issue of we're not keeping these arrays that might have deleted spots in the middle, right? Our array needs to be as compact as possible. So boom, it's still linear time to either add an element or remove it. Okay, so that's these two right here. Okay, and then for a linked list, it's linear time largely because they're linked lists. Okay, basically same case as in the ordered container. So removal is linear time for an array, even if you have the iterator. Okay, for the same principle, we're assuming that if you remove something from the middle of the array, keeping it as it's probably like the third or fourth time I'm saying it, just so it's clear. So hopefully it's clear by now. Keep it as compact as possible, so I still need to shift everything if I remove in the middle, end up removing in the middle. And then linked lists, it's either O of n for a singly linked list or constant time for a doubly linked list. Then you have the find operation. This is where a sorted container would shine, right? The find operation would be really fast. It would be log n time, right? Because I would take advantage of the sorted constraint and exploit binary search whenever I need to find an element in the container. Okay? Can't do that if it's a linked list because I still need to traverse no matter what. And I also can't jump. I don't have random access. Can't make jumps. So I still need to traverse. Takes linear time. Then dereference operator is just constant time. It's always constant time. Random access, which is open and closing square brackets. This is where array will shine, and it's O of 1 time, right? It's constant time because I can use pointer arithmetic. It's linear time in a linked list because I still need to traverse. Don't really have random access. And then the insert after and insert before is not available. It's not available in the, in this sorted container concept because if it's following some specific sorted constraint, having something like insert after or insert before would potentially violate that constraint, right? If you give someone the option to potentially use insert after or insert before, there's no way that you can ensure that what is being inserted follows the sorted ordering constraint. Okay, so they're basically not available. Cool. I think Frankie is asking, how is remove O1 for a doubly linked list again? Well, because if it's doubly linked list, right? So let me draw here. So if it's doubly linked list, node here, node back. There's another node. If it's a doubly linked, I mean, this one just goes to nothing, and then this one just goes to nothing. If it's a doubly linked list, yeah, is constant time because this, and I'm gonna use how can I use a different color here now? Because I'm not in my usual presenter view, so I don't know how to switch colors on my pen. But the point is, this because I have the arrow pointing to the previous node, I can easily reconstruct my list after I remove the element in the middle, right? All I would need to do after removal, this would mean that my list would now look like and I'm able to reconstruct it so that it looks to the picture that's on the right because I have access to this previous arrow right here and because I have access to this next arrow right here in the middle of the node that I'm looking to remove, right? So I'm assuming that I want to remove this guy in the middle. So it's constant time because it's a matter of just updating the pointers. That's it. Okay? Does that make sense? Was it Frankie? Can ordered and sorted, so good question by Sahil. Can ordered versus sorted be understood as partially or totally ordered? No. Just the mapping of ordered and sorted to what I mentioned, which is mathematical definition of ordering, partial and totally ordered. There's no mapping between those two. Those are completely separate concepts, right?
there is the STL container specifics that we're discussing here, and there's the mathematical concept of ordering, which is completely separate. Do not mix the two. It's very easy to get confused there. Okay? Okay? Because EECS breaks every rule normal people live by. Yeah, maybe. Hey, that's I can't argue with that. That might be true, especially with math, right? Okay. All right. So let's keep going because got a couple of things to still cover today. I might not get to unifying today, which is okay. Usually the merge sort lecture, which is a week and a half from now, it's always like half a lecture. So if all the material kind of shifts a little bit, it's completely fine. We'll be right on time for finishing lectures as we intended the schedule before the exam. All right, so ordered and sorted containers. Let's look at the usage of binary search because this is something that you will use in Project 2. Okay. All right, so binary search as a concept is fairly simple. It's, like if you had a dictionary, although chances are you've never used a dictionary. This generation doesn't even use dictionaries anymore. But if you had a dictionary, which is a book, right, with a bunch of pages in it, and then you need to look up a word because it's in alphabetical order, then, you can just open the book, see which page you're at, and decide on which half of the book is the word that you're looking for. Where is it at, right? Comparing to whatever words are in the current page that you're looking at. Or if you happen by chance to open at the right page, then you're done. You found the word that you're looking for. All right. So let's say that, let's look at this example for binary search. Let's say we need to find the value 21 in this array container that is shown on the slide. Okay, and notice that for binary search, we're always assuming that it's an array or a vector, never a linked list, because all of this breaks, it doesn't work. None of this works for a linked list, okay? Only for arrays, /vectors, /dex, okay? All right, so if we're finding 21 right there on the slide, first thing that we would do is find the element that's in the middle of the array. Visually, that's very easy to find. It's 13. And of course, what we would want to do is do some math, right, to find what the mid element is. But visually, it's just 13. And then compare, hey, is 21 greater than 13? Yes, it is. All right, so that means that I can just forget about the left half of the array. And what remains as interest to me is the right-hand side of the array, because I know that's where 21 is at. So now I look at that right half and find its middle, right? But of course, it doesn't look like the middle right there because there's an even number of elements on the right-hand side. So you're always going to run into this. So you need to take care of it when you're finding the mid. Depending on the implementation, you could have picked the mid to be 31 here, right? But by conception, it's usually the one on the left, so it would be 25. 25 is the mid for these 4-element array. So compare against 25, I see, 21 is less than 25, so I need to look to my left. And then all I have left on my left is just one element, which is 21, right? And I would then check, I only have one element. Let me see if it's 21. If it is, I found it. If it wasn't 21, I would have said, there's no 21 in this container, okay, this array. Cool. Very simple. You've probably already seen this before, okay? And what is the asymptotic complexity of the search? Well, you also probably heard this before because every time reducing the amount of elements that I need to look at by half, this is a log n algorithm. Okay, so not an n log n, this is an log n algorithm. Okay, so it's really fast. Okay, and I'll say this side note because I often get this in office hours. Students often confusing n log n with log n. Okay, n log n would be I do n binary searches on my container. right? If that's the algorithm, then that's an n log n algorithm because you're doing n binary searches. Each binary search is log n, so you get that n times log n. But if you're just considering the binary search algorithm by itself, then it's just a log n algorithm. Okay. All right, so that's fairly simple. That's binary search. Okay. And of course, for binary search to work, it needs the elements to be sorted. Okay. And this is, by the way, the concept of sorting here, although for the purpose of this course, we're only, for the most part, looking to sort integers, it need not be just integers, right? It's some sorting, some specific sorted ordering that should be satisfied by some generic set of elements, not necessarily just integers. But of course, integers are always the easiest example to use. But you can generalize this, again, for any type of complex elements in a container. All right, so here's the implementation for binary search. Okay, and what we're going to do now is basically look at better ways to implement your binary search. Okay, so suppose that you have this very, like if I told you, hey, go implement binary search, and you took a couple of hours, and you might have arrived at something like this, right? Of course, it's you implemented it as already knowing what the algorithm is, right? Because if if you didn't know anything about the algorithm, that'd probably take longer to figure out. I couldn't figure out in 2 hours. But if you told me what the algorithm is, implementing it, yeah, sure, a couple of hours. And this is probably what you would come up with. Okay, so you're given an array. Again, just to keep it simple, it's just an array A. There is some specific value that you're looking for. And then you have the bounds of what you're currently searching for. That bound is given by left and right. Okay. So my binary search takes up 4 parameters. Now I want to remove what I wrote, and I don't know how. Dang it. All right. So I don't have a percenter v. All right. So while I have those bounds, okay, left and right, I want to be doing the binary search on this specific bounds. Okay, or a specific range is a better way to put it. So while right is greater than left, which means that while I still have some range to search, okay, that's what it means. Okay, so line 3 translates to while I still have some range in my array to search. Okay, which it translates to that because all I'm checking is whether the right, call it pointer. Even though it's an integer, which corresponds to an index, we can call it a pointer because it's an index that's pointing to some element in the array. So if my right pointer is still to the right of my left pointer, so they haven't crossed each other, then I still have some range that I still need to search. Okay, so if that is true, then what I would want to do in line 4 is compute this mid element, which I can do by just doing left plus right minus left. Again, because of the check in on line 3, right is always going to be greater than left, so I won't run into any negatives with this right minus left difference. And then divided by 2, the fact that this is integer division means that if it's not the element exactly in the middle, it's going to be the one to the left of where it would be in the middle. Line 5 is if I found what I'm looking for, I'm done, boom. And I know the position in which I found that element, so I would return it. So by the way, this binary search function, what it's returning, it's the index of where the element lies in the array. Now, if the value is less than the right-hand side of the array, so excuse me, that was completely wrong. If the value is less than the value that's contained in the middle, right? So that means that it's in the left-hand side of the array. Then I just update the right pointer. Otherwise, I would end up updating the left pointer, which if I'm falling into that case, it would need to be mid plus 1. And that goes because of the calculation of the mid element in line 4. Okay, so you would have to include the next element after the mid. So that's what you're going to update your left pointer to. And then if you run in this while loop through and you didn't execute line 6, which means you didn't find the element, then I would return -1 to say the value was not found. Okay. All right. So if we can look at this code in terms of runtime, you have if we assume that n is the size of the range that I'm looking at, so it would be right minus left. That's what we're assuming is whatever, n. Each time I'm splitting by half. So that means that I have a total, like if I were to count all these steps right here, okay, and I'm looping k times, okay, but k, assuming, and this is my particular assumption to make the math easy for computing the runtime. I'm saying that n, I'm going to describe it as being 2 to the k, right? There's no specific reason for that. I'm using that assumption so that it's easy for me to then say, all right, well, if the number of steps is in the order of k, and I'm assuming that n is equal to 2 to the k, that means that k is log n, right? Because this kind of implies that k equals log n. And there is nothing in the code that tells me that this is so, right? I'm just making the assumption that n is the number of elements. That's the number one assumption. And that said number of elements is in the order of 2 to the k, right? I'm specifying that that's the case so that this math works out, okay? So the asymptotic complexity is log n. Boom, so those are the specifics. And you might, as I was mentioning earlier, all of this, even though we're picking integers, you can generalize to more complex objects. If I needed to compare more complex objects, how would you do that? Well, that goes to the previous lecture, which is the usage of function objects or functors. Okay, so we had this example in the previous lecture where, say that I have a struct that's a point, right? It contains a pair of integers, but I might want to sort point by either the x coordinate or the y coordinate. And so I would provide it as part of my implementation for point. I would also provide functors that would facilitate comparisons by only the x coordinate or only the y coordinate. Okay, and so those are examples of how you can end up sorting more complex objects. Okay, so how about if we needed to speed up binary search? And in fact, it's interesting because this is how the binary search in STL works. Okay, and more on that in a little bit. Okay, but before we get to that, if I wanted to speed up binary search, I could look at the code that I had in previous slide and be like, well, the first thing I'm doing is comparing to see whether I found the element. Okay, where, well, clearly, finding the element occurs much more rarely than all the other elements, right? There's only one of the elements that I'm looking for, and there's a bunch of other elements that are not the same as the element that I'm looking for. So if I check whether the element that I'm looking at is the one that I found, I'm going to end up making that comparison a bunch of times, but it's only going to be true once. So it's rarely going to be triggered. So why do that first? It's a bit wasteful. Basically, don't check whether the element that I'm looking at is the one that I'm currently looking at is the one that I'm looking for. Don't do that first. Basically, do it last. And that's a bit of an optimization on binary search that STL does. Okay. So this is the code that we had earlier, right? If you see in line 6 and 7, that's where we're making the comparison. If the value that I'm looking for is equal to the current element that I'm looking at, which is going to be the mid element. Okay, that's the very first thing that I'm doing in my while loop after I compute the mid. Okay, so I want to kind of shift things around or refactor my code to avoid doing that. So what I can do is basically, all right, so I'm just going to check instead whether mid is less than val. I'm going to do that first. Conversely, you can reorder this if statement to, do the check in line 8 first. I mean, it would be up to you. So, but here we've chosen to check whether mid is less than val. We're going to do that first. Okay. And so that means that there's a lot less comparisons against mid that would occur. In fact, I wouldn't even need to compare against mid, because if it's not the case that's in the right and not the case that's to the left, then it means I found the element and I can just return mid. Okay. So that's one optimization. So that means that I've now narrowed it down to 2 comparisons rather than 3. And yet another optimization would be to instead of having a binary search function, make it a lower bound function. Okay, and then I don't need to worry about comparing against mid at all. So I don't need to check equality at all. And in fact, this is how binary search in STL works. There is a binary search function in STL, but it just returns a Boolean, which is oftentimes quite useless. I mean, it could be useful if you just want to know whether the element is in the container, but oftentimes you want to know whether the container is in there and also know where it is at, right? So that's where the binary search STL function is kind of useless. It only returns a Boolean. Whether you rather want to know where that element was found, so you want to return the integer that's the index to where that element is at. Okay, so this is now what it boils down to. There's just if and else. There's no if else at all. Okay, but that means that what I end up returning, right? So if I escape that while loop, it means that I just return whatever is left, and this is both a pun and the actual code, right? I just return whatever is being indexed right now with the left pointer, and then whether we determine that that is in fact the element that I'm looking for is now outside of the scope of this function. That's why we've changed the name from binary search to lower bound. Okay, because all it's going to do is return an element that it's either equal or less than. Okay, so it's up to you after the call to lower bound to check whether it is indeed the element that you're looking for. Okay, so that's going back to STL. That's what we end up using most of the time to do a binary search on a vector or a deck, is the lower bound function rather than binary search, because it just returns a bool, okay, not the location. And then furthermore, we have in STL an upper bound function, which is similarly is going to return the element, the first element that is greater than the element that you're looking for. Okay. All right, so let's look at how this works, because I will tell you right now, you will be using upper bound in your project too. So please pay attention to how this lower bound function works. It's really not that complex. All right, so this is, let's say that we have a call to the lower bound function on this array, and notice that I give the range as just being begin and end, right? And the value that I'm looking for is 7. Okay. Well, in this call, what's going to happen is, all right, I'm going to find the mid, which is 13. So compare 13 against 7 and determine that I just need to continue searching the left-hand side of the array. Then compare against 3. That's my new mid. 7 is greater than 3. So therefore, I just need to search the right-hand side of that subarray. And rinse, repeat, compare against 5, determine that it's greater than, and then boom, I've arrived at 7. Okay? So lower bound, if the element is in there, it will find it. Okay? Again, it won't tell you that I found it. It'll just tell you that, hey, this is the index to the element that I found. Right? So here, it would not actually return 7. It would return, assuming 0 indexing, right? 0, 1, 2, 3. It'll return 3. Okay? And it'll say, all right, the element that you're looking for, I found it to be at 3. Now, it might or might not be what you're looking for. It's up to you to check whether it's indeed 7, because I could have arrived at a different value, which would mean that 7 is not in the array, right? If I arrive at something other than 7, if by I mean the lower bound function, if the lower bound function arrived at an element that's different than 7, it means that 7 was never there. Okay, so that's the next example in the next bullet point, which is I'm going to look for 26. Okay, so mid again was 13. I determine that's on the right hand side. Compare against 25. Determine that's on the right hand side again, and then find the mid, which is 31, and then that's it. What I would return here with this lower bound function is 7. Okay, the index to the element that I found as the lower bound. But you can see that it's not 26, right? Again, lower bound is going to return either the element if it's there, but if not, it's going to be the next element that is greater than 26, which would be 31. Okay, but if you're strictly looking for whether 26 is in there, then you would compare 31 against 26, say, oh, they're not equal, so therefore 26 was never there, and indeed 26 was never in the array. All right, so upper bound, interestingly enough, is never going to return the value that you're looking for. Okay, this is not the value that you're looking for. Like a Jedi would say, sorry, that was very nerdy. But anyway, upper bound, if I'm looking for 21, it would compare against 13, look at the right-hand side, compare against 25, determine that's on the left-hand side, and then get 21. And in fact, sorry, not get 21, but compare against 21, and in fact return 25. Okay? That's upper bound. And so notice that even though 21 was there, I'm returning 25 because you're trying to find the next largest element after the value that you're looking for, right? So that's why even though I passed 21 here, what it returns is 25 is the next largest element after 21. And then if you did upper bound trying to look for 4, which is never in the array, then I'll let you run through the animation, but it'll basically return 0, 1, 2, right? It'll return 2, which is the element that has value 5. Okay, so I suggest do play around with these functions outside of the context of your project, okay, so that you're very familiar with them. I feel students often, we give you all this information and then you immediately start using lower bound in your project without really understanding how it works, and then that runs you into trouble. So just, play around with it. We've given you code to generate a vector of random integers, pass it to lower bound, see how it's working, be comfortable with it, and then go ahead and make use of it in the project. All right, cool. All right, so we'll finish today with representing sets. Definitely Union Find we'll discuss on Thursday. All right, so we discussed the notion of having searchable containers, right? Those, we didn't mention this in the beginning, but those are otherwise known as sets, right? If you have a container where the objective of the container is to facilitate EC query or EC finds or EC lookups, however you want to call them, right? By EC here, we also mean that they're fast, right? So the find lookup operation is real fast. Okay, we want to make it that way. In a lot of languages, those are known as sets. Okay, and beyond just facilitating the a fast find function, there's also a bunch of other operations that we would want to do on sets, right? So things like union, intersection, set difference, symmetric difference, and all these definitions, if you harken back to your 203 days, those are, the same as opposed to the ordering that I was talking about earlier. Here, the definition of set union, set intersection, set difference, and symmetric difference, all that does map with the concepts that you have in discrete math. Okay, there's no difference. They basically build the STL such that those definitions match what we have in discrete math. All right, so you might be, oh my God, that is so much stuff that we need to worry about in terms of searchable containers or sets, right? However, so I'll use the word sets. It's easier to say than searchable container. Okay. The only operation that we will care about is, or at least for this lecture, will be the union operation. This is the one that we will discuss in detail. Okay. Intersection, set difference, symmetric difference, those are available, right? And also you have add element and is element. So is element is the function that's analogous to find, lookup, okay, search. The union operation is of particular importance, okay? So what do we mean by union? Well, if we have two separate sets, we want to, out of those two sets, create a larger set that is now composed of both of the two sets that I was given as input. And the output set is also satisfies the same constraint that the two input sets follow, right? That's what we mean by union here. Okay. So assume that we have two sorted sets, say their names and the sorted constraint is alphabetical order. So we have set 1 shown there on the slide and set 2, okay? And then the output set, we're going to call it set 3, okay? So what set union would do is, okay, so I compare my first element in set 1, which is Amy, compare it against my first element in set 2. So the blue arrow is basically the iterator or pointer to the first set. The red arrow is the pointer or iterator to the second set. The green arrow is an output iterator. Recall from the last lecture that there are such things as output iterators, right? So it means it's the iterator to the currently empty set 3. Okay, so I compare Amy and Amy, okay, determine that they are equal, and I basically put a single Amy in set 3. So this is what union does. It's not going to put duplicate elements in the output set. So I would place one Amy, and now because I've done inserting Amy into the output container, I can move both my blue and red pointer to look at the next elements in each of the input sets. So now I'm comparing Beth and Blake. Of course, here I would determine that Beth would be the next one up. So that's why what I insert into set 3. Move that pointer, the green pointer, I've already moved because I basically decided, I've inserted my second element, so I move my pointer there, okay? And because I ended up inserting Beth, I would also move my blue pointer, but notice my red pointer stays in place because I have not inserted Blake yet, okay? So now I'm comparing Brian and Blake, okay? And determine that Blake should come up next. So that's what I insert, move my green pointer, and now I'm comparing Brian and Bob, determine that Bob should be next. So I insert Bob into the output container and move my red pointer only. Notice blue stays put because I ended up inserting Bob, which is in the second set. I move my red pointer. But Brian still in the set 1. So then I'm done with set 2, right? There's nothing else to compare against in set 2. So now I would say, okay, so I'm just going to insert Brian. And in fact, all I need to do is just insert everything else that's in set 1, right? So I just continue moving my blue pointer along, inserting everything that's in set 1 into my output set. Okay. So that's set union, right, of two sorted ranges. And by ranges here, really, you can also think of it as, two sorted containers, because, that's what we're doing. But we use the term ranges here because notice that we're relying quite a bit in the pointers, the blue, the red, and the green pointers, which again, when it comes to implementation, we don't want to use pointers. We want to use iterators. Okay? So that's the code for basically implementing the example that we had before, but using iterators. Okay? So notice that you have first one and last one right here. Those are the iterators that correspond to set 1. Notice, in the example, we only had one pointer, but it's because of simplicity. But at all times, the code does need to be aware, where set 1 ends. So even though if I go back to the beginning, right, at all times, we actually, and pardon the fact that this arrow is going to be red, right, we also have pointers to here, right? So that's why in the code, right, again, we didn't have those arrows there for simplicity. Those arrows actually never move, but we still need them because we need to determine with our iterators, when are they done, right? When they have reached the limit of the container, okay? So that's why we need them. So that's why you have 2 sets of pointers for set 1, 2 sets of pointers for set 2. Then the output iterator, okay, that corresponds to the green arrow. And then you're given the functor for how to compare, right? So this is kind of a generalized templated function. So it says like, I'm not assuming that these are integers or strings specifically. You need to give me a compare a functor so that I can compare these elements, okay? Whenever I dereference the iterators. All right, so I'll stop it here because we're a bit over time. I think we're just right on time because we started a few minutes later. So I'll continue here on Thursday. I'm sorry I could not get, there's probably a bunch of questions there. I'll make sure to have somebody on the chat on Thursday to answer questions. Basically what we have remaining in this lecture is union find, so I'll start with that in the next lecture. Again, do not worry too much about it. It often happens with 281 material that there are slips, but I'm sure I can get through all the material that we need before the exam. Okay, and if we don't get through all the material, then we'll leave material out of the exam. We can always do that. All right, so everyone have a good afternoon. Stay warm and safe. My kids, it was a virtual snow day, which sounds like an oxymoron to me, but that's what they had. Of course, we don't have snow days in Michigan, but do start project 2 again as soon as possible. All right. You all have a great night, great afternoon, great night. See you on Thursday.